for joining this sport lecture, sir. Uh, he has a vast experience in nanocrystals, which leads to, you can say, you can say a battery, or you can say advanced battery concept can be generated from nanocrystals or nano manufacturing or nanosynthesis. So I would like Manjeet, may you introduce sir formally.
Good morning, everyone. Am I audible, Deepak sir?
Yes, perfect.
Okay. On the behalf of organizing committee for this FDP program, we would we would like to welcome Professor Samir Sapra and express our gratitude towards him for sharing his knowledge, experience, and wisdom with all of us today. The broad area of his talk would be around smart material technologies. Professor Samir Sapra has joined the Department of Chemistry of Indian Institute of Technology, Delhi as professor in 2018. He did his PhD in the field of electronic and optical properties of semiconductor nanocrystals from Indian Institute of Science, Bangalore in 2004. He has a professional experience of 24 years at various positions at IISc Bangalore, Cookson Indian Research Centre Bangalore, LMU Munich, TU Dresden, and IIT Delhi. He has an expertise in the field of electronic and optical properties of semiconductor nanocrystals. He also has an expertise in fabrication, measurement of LEDs, and solar cells. He also has proficiency in operating X-ray photoemission, ultra-high vacuum systems, and Photon 77 programming. He has contributed more than 50 publications in international journals, book chapters, and conference proceedings. He has been awarded with National Talent Search Examination India, AVH Germany, and Outstanding Young Faculty Award at IIT Delhi. Now, with these words, we would request Professor Samir Chapra to kindly take this session so that we can benefit from his lecture. Please, sir.
Thank you so much. Thanks again, Professor Singh and Professor Qasim, for your kind invitation here. Okay. Sorry, I I thought my lecture is at 10:30, but
No, it's fine, sir. You are,
okay. How long do you want me to speak?
um, so it's about a 90-minute session is there. So
Okay.
it's up to you when you stop and give a 5-10 minutes for a questionnaire session.
Yes. Okay, I'll do it that way. But what I'll suggest is that if anybody has any questions, you can stop me in between and you can ask me. Uh, is that fine with all the participants? Yes? Okay. Because, yeah, if you have a question, then please go ahead. Okay, so let me share my screen. I hope something is visible and I'll share my slides.
Yes.
Okay. Um, so yeah, good morning, everybody. And well, I'll be speaking on two-dimensional nanomaterials today. So these are a very upcoming class of nanomaterials, and I'm sure everybody's heard of graphene. Yes. Um, I'll talk of mostly a semiconductor nanomaterial today. Okay. And later on, if you have any doubts, you can always email me also to ask. But so at the very outset, what I always do is to acknowledge the people who've been involved in this research. And in particular, I'm going to present the work of my PhD student, Dr. Shamim Hassan, who graduated last year, is now doing a postdoc. And the work is now being followed by Ajit, um, Sahil, and Varsha. So mainly Shamim's work is what I'm going to present, and my collaborators Praveen, Ritu, Shashwata, and Samit, who've been involved in these projects. So I must thank them. Very heartfelt thanks to all of them. And the funding agencies, DST, DRDO, SERB, and IIT Delhi. Okay. So we have a very good central research facility at IIT Delhi, and a part of this central research facility happens to be in Sonipat, so which is closer to DTU. So, and this is open for everybody. I'll show you some results from the central research facility equipment, and everybody across India can create a user account, log in, and use it. All right. So most of the attention that goes from us material scientists is basically towards energy. Well, and we continuously worry about how to convert energy, how to store energy, as you were saying, batteries, how to utilize energy in a smart way so that you have minimal wastage, and then finally do some cleanup act. So, in our lab, we are particularly working on solar cells, hydrogen generation. We are working on LEDs. We work on photocatalytic degradation, conversion, and we are starting with carbon dioxide conversion as well. So these are the kind of activities that go on in our lab. And all these activities are essentially centered around nanomaterials. Okay. And the kind of nanomaterials that you see over here, this is a picture of cadmium selenide quantum dots. All are cadmium selenide, but they are all of different sizes, and therefore they emit different colors. I'll tell you more about this in a while. So, well, this is just one kind of nanomaterials. We deal with many other nanomaterials, and we'll discuss a lot of them today. So all these nanomaterials that we deal with, their dimensions are typically on the order of between, let's say, 1 nanometer to about 6 nanometers, 7, maybe at the most we can put 10 nanometers, something like that. And when you are at that dimensions, you have a lot of atoms on the surface. Okay. So we study a lot of surface property relationships over here. Okay. And of course, there is the size property relationship, the quantum size effects that come in. The quantum size effects that come in. And each of these nano particles happens to be different from the other one. And therefore, we also do a lot of single particle experiments. For example, if you look at this video over here, you can see all these particles blinking. Some are green, some are red. Well, so you do try to do a lot of statistical, you apply your statistical approaches to understand the properties of these particles. Then we go into some applications of these materials, then studying the basic fundamentals. And one of those applications that we deal with are photovoltaics and photocatalysis. So in our small chemistry lab, we don't really try to make silicon solar cells, but what we make are something called dye-sensitized solar cells or quantum dot sensitized solar cells. And we are starting with the perovskite solar cells. Okay. And in catalytic efforts, we go towards water splitting, where we use hydrogen evolution reaction or the oxygen evolution reaction, right? Of late, for the last 4 years or so, we ventured into perovskites, and that's how the perovskite solar cells are coming in. So these perovskites are very interesting materials. In 2009, They were discovered, well, they've been known for a very long time, of course, more than 100 years now, but they were discovered for applications in solar cells. And these are the organic, inorganic, lead halide based perovskites. Okay. So we are trying to, there are two problems with these perovskites, although people have already demonstrated 24-25% efficient solar cells. But the two problems are, one, that it contains lead, the second, that it's unstable. So we are trying to address these issues of getting rid of lead by getting into layered materials and double perovskites, and also addressing issues of stability of the lead halide, of the halide-based perovskite materials. Also, they are very, very luminescent materials. Okay. All right. Then in the past, we've been a lot more active with light emitting devices. Okay. In particular, we've worked a lot on white light emitting devices. And this particular picture shows you that you can tune the white light emitting device right from the bluish, with a bluish tinge towards the yellowish tinge, what you know as, in the market, what you know as cool daylight and warm daylight. So these devices, these light emitting devices based on quantum dots are now found in televisions. Okay, so this is research of some distant past actually. We do make some LEDs now, but just for demonstration purposes. We've been involved with a lot of sensors. And for example, biosensors, ethanol sensors, and sensors based on transistors. So for gas sensing, for anion detection, so on and so forth. This particular example, what is shown over here, is that of single-stranded DNA attached on quantum dots, and which provide a very, well, essentially a lot of surface over there. So a lot of these DNA molecules attached over there. And then well, this particular sensor is from a work which was to detect chronic myelogenous leukemia, CML. And in fact, it was in collaboration with Professor B.D. Malhotra, who was at DTU for a very long time after he retired from NPL. So the second strand, which is complementary, comes from the patient who's suffering from leukemia. So what you've done is to take the single strand, which has a base pair sequence of, whatever that AGCT is, it's complementary to the one that is coming from the patient. So this quickly zips up, and then you put the redox reagents over there and see the redox activity, which means you get a change in the current values. Okay. And by monitoring these changes in the current values, you can make amperometric detection of the single strands that are coming in, which essentially means that you can differentiate between positive and negative patients. All right. Also, our nanoparticles have found their way into some of these poor mice, which you see over here. Is my cursor visible, by the way?
Yes, sir, it is visible, sir.
Okay, great. So these, for example, these nanoparticles are magnetic nanoparticles. Now, by the way, these leukemia sensors, we'd used gold nanoparticles and also quantum dots. Here we have magnetic nanoparticles, which are used to localize these nanosomes into certain regions. Also, you have, along with the magnetic nanoparticles, you also put fluorescent nanoparticles, so you can also do fluorescence imaging. So both MRI and fluorescence imaging is possible over here. And we localize these particles to the regions where there is tumor. Okay. But all these three things that are shown in yellow are mainly done in collaboration with other laboratories, and we don't make the LEDs ourselves as such. I mean, we do make some very, very basic devices, but not the LEDs. And we also have sensors and definitely not the bio applications in our lab. Okay. So these are all very good collaborators. what I'm going to tell you today is essentially about these two-dimensional transition metal dichalcogenides. Okay. These are analogs of graphene, for example, molybdenum sulfide, molybdenum selenide, tungsten sulfide, tungsten selenide, tellurides, niobium. I mean, you look at the first row, second row transition metals, and you can take their chalcogenides. And a lot of them make these sheet-like structures. Okay, I'll tell you about the structures and then you'll understand what exactly I'm talking of. So we make these, we make a lot of heterostructures of these and then try to find applications. And the applications in particular can be photoconductivity, can be water splitting, can be other catalytic activities, which I'll come to. All right. So the outline of the talk for today would be that there'll be a brief introduction. Well, uh, I'll try to make the introduction less than brief, more, so slightly more, so that if it's a new topic for a lot of people, then they would appreciate it much. Then I'll go on to these 2D transition metal dichalcogenides and their heterostructures and tell you about some of the applications which they have been applied for. Okay. So let me start with molybdenum sulfide. In fact, why molybdenum sulfide? Because it's the most studied one. Although I'll be talking on molybdenum selenide, but this one was the most studied one and of course the first one. Also, it's very, very naturally abundant in the Earth's crust. Okay. And the one that is abundant is called the 2H polytype. I'll come to that. Okay. And even before this boom in the 2D transition metal dichalcogenides, molybdenum selenide has been used for very, very long. You see this. Okay. Earlier, it was used as a dry lubricant. I remember having used it in my BSc chemistry lab. Okay. Also as a catalyst for a lot of reactions. A lot of organic chemists do know about these catalytic applications. Okay. And for lithium-ion batteries. But if you look at this graph, which tells you about the number of papers, till about 2010 or so, this graph has been rather flattish. And this is 2004-5 when, 4, I think, when graphene was discovered, and 5 when the same Scotch tape method was applied. So those of you who do not know the Scotch tape method, it's you put the Scotch tape, yeah, on top of these layered materials, pull it up, and you'll get a few monolayers of the material stuck to the Scotch tape. Then you take the Scotch tape and put another Scotch tape and then put another one and do this for a number of times, and finally you have 1 or 2 monolayers of the material that you desire. So this is about 2005, and then a lot of efforts started going into development of these 2D materials, and you see off late there's been this huge rise in the number of publications and in the number of research activities that go on in these materials. Okay, so something about the molybdenum sulfide, and in general this is true for whatever I'm telling you is true for all the semiconductor transition metal dichalcogenides. Well, there can be some semiconductors, some insulators, some metals, and some semi-metals, but today I'll just deal with these semiconductors. It's a direct band gap material, 1.9 electron volt band gap. That is a single monolayer MOS2. When you go to multi-layers, it becomes an indirect band gap material. So, it completes the basket because you have a conductor, which is graphene, you have an insulator, hexagonal boron nitride, and now you found a semiconductor. And therefore, making any of these low power devices in electronics becomes possible. Nobody's saying that you'll replace silicon, but then you have some more alternatives. Okay. And people started using a lot of these materials for other applications too. The structure of these transition metal dichalcogenides in general, they are found in these 3 polytypes, 1T, 2H, and 3R. So if you look at the top layer, This 1T is octahedrally coordinated. 2H and 3R both are trigonal prismatic. But if you know of the packing sequence in close packed structures, it is either A, B, C. So, you put all the balls together in one layer. So one ball is surrounded by 6 balls of identical sizes. On top of that, you have some voids. If you try to put more balls on top of it, they'll fit into these B-type voids or C-type voids. And again, on top of that, again, you can have balls fitting into A-type or C-type if you put in B. So if you have this ABC kind of packing, then what you get is a 1T, which is a tetragonal structure. The 2H is a hexagonal structure, but you need 2 monolayers of molybdenum selenide, sulfide, whatever, in order to describe the complete unit cell. In 3R, the rhombohedral structure, you need 3 monolayers. So this is the kind of packing: AB, A, B, C, B, C, A, C. Again, A, B, A. So that is the repeating unit. Why does MOS2 go into either of these polytypes is a question. Well, of course, this is trigonal and this is trigonal. So one won't be able to, there's going to be a subtle difference. Very difficult to distinguish this, except for some energy considerations. But why octahedral and why trigonal? And that is understood very easily. I'll tell you about that. Okay. Also, you can have distortions. I will not worry about distortions, but some distortions I'll show you later. Okay, so this is what the structure is, as I've told you. The distances, well, essentially, if you go back, the distance within the plane is small compared to the distance between the planes. So intralayer and interlayer distance. This is van der Waals distance of about 3.5 angstroms, and this is about 2.5 angstroms. So, okay. So I was telling you about these coordinations. It can be very easily understood if you know the basics of crystal field theory in chemistry. Well, even if you don't know, because I believe there are a lot of non-chemists over here. So if you look at d orbitals, there are 5 d orbitals, okay? And these 5 d orbitals, in the presence of an octahedral field. Now, octahedral is the way it is shown over here, okay? So 2 of these, so X, Y, Z is shown over here, you can see. So if you have this octahedral field, then, all these ligands, they approach at X, Y, Z, and the dx square minus y square and the dz square get higher up in energy. The other 3 d orbitals go lower in energy. So this is known as the T2G and EG splitting. Now, okay. So if you have molybdenum 4 plus, that has only 2 electrons, and 2 electrons would go into the T2G level. Okay, but this fellow, these 2 triangles can get distorted, and the moment they get distorted, they go towards the XY or the YZ and not the XZ. So distortion essentially removes the symmetry, and this level comes down. Well, if it gets highly distorted, which is, completely rotated and make it, so this is a staggered arrangement, this is an eclipsed arrangement, so make it completely eclipsed, then it takes over the trigonal prismatic, whose energy levels are like that. Okay. So if you have only 2 electrons, then you can see that this particular arrangement has a much lower energy, is more stable, or the distorted also has a slightly better energy arrangement than the undistorted octahedral. Okay, and therefore, when you have 2 electrons, you have this. But then how does the 1T polytype come? The 1T polytype comes in the presence of some of these metals. For example, When you want to make 2D materials, you take the bulk material and you have to exfoliate it somehow. And people do it in the presence of lithium. Now, what lithium does, the lithium metal gives off an electron to molybdenum sulfide. Okay. And it comes and sits between the layers. Okay. So it exfoliates the layers, it expands these layers and throws them apart. But it sits over there with the electron coming in over here. Okay. Now this scenario becomes more stable and the 1T polytype is then stabilized. In fact, the 1T polytype in the presence of lithium is, well, the 1T polytype is known to be metallic. And it was discovered it's because of the electron of the lithium that comes in that this metallicity is, the metallicity comes about. Now, when you go and make these materials, you need to characterize them. And some of the characterization tools, one of the easiest one is do a UV absorption spectroscopy. And all of these semiconductors, you would see these two peaks, the A peak and the B peak. Okay. In case of molybdenum sulfide, it's at 640 and 580 nanometers of 1.9 and 2.1 electron volts. Okay. So you'll see these two peaks clearly. Also, if you do Raman, you would see these characteristic peaks. The E peaks are the twofold degenerate, which means they are within the plane. And the A peak is out of the plane mode of these 2D nanosheets. The values are very characteristic. So you can use these to essentially, to characterize your material. All right. Now, because of this fact that you have 2D layers, okay, the charge transport properties also are very dependent on which direction you're moving. So if you are in the 2 dimensions, then you have very high charge carrier mobilities. Okay, this is 100 centimeters square per volt per second. These are very large numbers. But otherwise, it's a semiconductor, right? But if you go in, across the layers, then the conductivity is very low. So you can apply pressure, go towards metallic state. As I said, with lithium, you can go towards metallic state. With rubidium, you can even go towards superconducting state. So all these things are possible. A lot of research papers are there. These materials are also very, very stable. Okay, very chemically inert, and that is because it's a closed layer structure, closed shell structure in the one monolayer, right? They're van der Waals layers, so you can just remove them and still you're not breaking any covalent or ionic bonds. You are very stable up to very high temperatures. Well, of course, if you use very strong solvents, aqua regia and strong oxidizing solvents, then there's sulfur, and sulfur tends to get oxidized, or selenium or tellurium, whatever. MOO3 is obtained if you also react with oxygen, but otherwise it's very stable. Okay, nothing happens as long as you want to work with them. So to sum up, you have a structure and properties of these 2D transition metal dichalcogenide nanosheets. These are the layered structures. Okay, all these layers can be exfoliated. And as I showed you in the first picture of nanomaterials that I can have different colors, essentially what it means is that I have a tunable energy band gap. The same thing is true with these materials. I'll dwell a bit more on that. And I've already told you there's a direct to direct band gap crossover. We'll mostly work with one monolayer sheets, so mostly with the direct band gap materials. The excitons are very strongly bound because they have to move in these sheets, and I'll tell you how strongly bound these are. You've already seen the excitonic peaks in the absorption spectroscopy. So if they're observed, which means they are definitely more than room temperature, but these are even strongly bound. Then you have a high mobility of charge carriers, high specific area, and because you have a high specific area, you also have high catalytic activity. So a lot of these applications based on all these properties can be thought of. This is typically the trigonal prismatic arrangement that I'm showing again over here with molybdenum in the center and the chalcogens around it. So you can think of a lot of applications. And if you look at these applications in green, these are based on the electronic properties. And in the literature, they've been called basal plane applications, although not much to do with plane over here. But I'll tell you why they have been called, because of the fact that the edges are the ones which have all the defects. And those defects are the ones that allow for some atoms from outside to come and attach over here, and therefore do anything that has to do with catalytic activity. So electrocatalysts, counter electrodes, these are all catalytic activities. And all these are based on the electronic properties of the material. So these are edge site applications and basal plane applications. We'll look at a few of them. The way to make these materials, there are broadly three different ways. One is simple exfoliation, the Scotch tape method, or you could even do it in a sonicator. You could even use some chemical exfoliation, as with lithium, I've already told you, NMP, and so there are a lot of these things. Well, each of these methods has its own pros and cons, so one should look at that. The physical methods, very, very expensive ones, CVD, NBE, but then you get very neat structures over here. Chemical methods, again, solvothermal, colloidal methods. The good thing with colloidal methods, and me being a colloidal chemist, I stick to my basics. The good thing about colloidal method is that we can get very high yields, and then it's substrate free, so I can transfer it anywhere. Okay, but there are some some cons over there. Okay, and I'll show you those. Well, but before I go into the results, let me tell you briefly about the synthetic methodologies. If you look at the synthetic methodologies, then we borrow our synthetic methodologies from the colloidal methods that we've learned over these years. And one such method is known as the high temperature injection route. So what you do, for example, this was a method from cadmium selenide again, or cadmium sulfide, or zinc sulfide, selenide, mercury, lead, lots and lots of these materials that we make. The idea is, if you're making cadmium selenide, then you take a cadmium precursor in this round bottom flask. You need a good temperature controller with a PID. You need a heater, you need a magnetic stirrer, and sometimes, well, most of the times, you need Schlenk so inert atmosphere conditions, so vacuum and argon. And there's a septum for injecting stuff and taking it out, since the entire system is closed. Now you have a cadmium precursor over here. Okay, so typically this is cadmium dissolved in a high boiling solvent like octadecene, or one of those that I've shown here, trioctyl phosphine oxide. Okay, and then you take, for selenium, you could take trioctyl phosphine selenium. Okay. Now, if trioctyl phosphine, it's a long chain thing, right? If it bonds to oxygen, it also bonds to selenium. And very easy, just you dissolve it, take it in a syringe, heat it to a high temperature. Okay, for example, heat it to 300 degrees, and then inject it very fast. Now, this is a solution at room temperature, and here you have 300 degrees. So there's a very vigorous reaction that happens at 300. What happens is cadmium reacts with selenium. It's got a very good affinity. Okay, and it immediately forms a lot of nuclei over here. Okay, at 300 degrees. Well, and then the temperature falls down because you've injected a cold substance into it, and it falls down to roughly less than 240. Okay, and when that happens at 240 or so, uh, no more nuclei is formed because that vigorous reaction will not happen. What will happen instead is that cadmium and selenium precursors, which are present in this solution, they get deposited on these nuclei. So essentially what you've done is something which has been known for 70, 80 years, 1950, the Lamer and Dinager growth models, where they say it's essential to separate nucleation and growth to have uniform colloids. Okay, so what happens is if you do not separate them, and when one of these particles has become this big, a new small nucleus gets formed, and you have a large polydispersity in size. So you need to control that. So you need to separate nucleation and growth, and then you'll have very, very monodispersed particles. Okay, and that's what you want when you want to study any property as a function of size. All right. Otherwise, you can also make, well, these were with organic chains. Okay. Let me tell you, these white things that you see over here in the model, these are all organic chains mostly. Okay. And these organic chains are the ones that passivate the nanoparticles. Okay. They electronically passivate, they structurally passivate. So they make it stable. And when they passivate it, then whatever the properties of these organic molecules are, so if you have these long chains like trioctyl phosphine oxide topo or stearate, cadmium stearate, right? Stearate is again C18 long chain, 18 carbon atoms. Then they have a propensity to dissolve in organic solvents like toluene, hexane, and so forth. But if you actually have some thiol chains, then the thiol, of course, would go and link to cadmium. But the R group, if it has OH groups or COH groups or NH2 groups in abundance, then they would be rendered water soluble. So depending on what kind of ligands you're using, you could make them soluble in different solvents. Okay. You can even tune them to be soluble in certain solvents and not other solvents. Okay, but anyway, you better use a high temperature route for having good monodispersity. All right. Now, making this high temperature route, I'm showing you results of cadmium selenide, and this fellow crystallizes in two different structures, zinc blende or woodsite. Well, woodsite is the well-known polymorph for cadmium selenide. But when you're making nanomaterials, it can either go into zinc blende or woodsite. Now, both of these structures are essentially cadmium tetrahedral. Yes. Is there a question? No. Cadmium is tetrahedrally bonded to 4 selenium atoms. And so selenium is also tetrahedrally bonded to another 4 cadmium atoms. Well, that one and another 3. If you look at these two different structures, zinc blende is a cubic one, woodsite is a hexagonal one, but the difference is actually a rotation across one of the atoms, about one of the atoms, by 60 degrees. That's all. You go from zinc blende to woodsite. Okay. So these different structures actually you can characterize using TEM, and you see that they are all of more or less equal sizes. This is what I meant by making size monodispersity. You can characterize them with HRTEM, high resolution, and all these equipments are available at the central research facilities. Okay, you just pay a small amount and get your stuff done rather than taming a white elephant in your own lab. Yeah, so all these things, you see 0.357, and this is the woodsite fellow, 0.350. You can actually match all these with the zinc blende or woodsite phases. So the presence of 002 is definitely woodsite. 111 is definitely zinc blende. So you could do the electron diffraction you can see all these X-ray diffraction peaks. Well, of course, they are broad, and I believe a lot of you understand what the Scherer broadening is. You can estimate the crystallite size from there. The only difference that you'll see is this 103 peak appearing slightly in CDSE woodsite and not appearing in zinc blende. But as you make the particle size bigger and bigger, you start to see three peaks appearing here and only one over there, and these peaks get narrower as the particle grows. Yeah. The other way of characterizing these materials is doing a UV absorption spectroscopy, and you'll observe that you start to see all these excitonic features, one, the second, the third, the fourth. Okay, same in both the cases. And you also observe fluorescence. Well, this particular fluorescence is in the yellow. By the way, the band gap of CDSE is about 720 nanometers. So this is much higher than the band gap, okay, lower wavelength. So these are known as quantum size effects. And these quantum size effects, one can very easily understand if one goes to basic quantum mechanics. And, the first problem is particle in a one-dimensional box. Okay. And you start solving your Schrodinger equation. You get your wave functions. The most important thing is to remember that you have quantized energies. Yes, Gaurav, tell me. Gaurav, you have a question? Gaurav, do you have a question?
I think, sir, he's just on his camera only.
Okay, now I'm getting some disturbance from behind. So if you have a question, go ahead and ask me. Okay. Yeah. So what you should remember is the basic thing is that your energy levels are quantized, and the way they are quantized um, is essentially this equation: n square h square by 8ma square, where a happens to be the length of the box in case of one dimension. If you were actually solving for a spherical particle, then a happens to be the radius. Okay. So a particle with radius a has its energies quantized as per this equation. Now, what exactly is this particle and what is the box? So,
बायोडेटा में है नहीं
so essentially, the particles that get quantized are the electron and the holes. Okay, and these electrons in the holes well, these are semiconductors. So the valence band is completely occupied and the conduction band is completely empty. So you don't have anything, but they arise when you shine some light on these materials and excite the electron from the valence band to the conduction band. Okay. Now you have an electron here and a hole here, and these electron and holes, they they are the ones that are confined in your entire particle, the nanoparticle. And that's why it's called a quantum dot, because you see these quantum confinement effects. So these are the energies given here for the electron and the hole separately, because both of them are confined and both of them show these quantum effects. And of course, these are charged negatively and positively. So you do have a Coulomb attraction between these particles. And of course, they can polarize the clouds of the nearby atoms. So you would also need to worry about these perturbative terms if you were to do very accurate calculation, but this is typically less than 1%. So the energy of a particle of radius r is the energy, so band gap essentially, is the band gap of the bulk material plus the quantum confinement effect minus, because Coulomb energy stabilizes, so minus the Coulomb term. And then you can get the relation of the band gap of a material of radius r with size. And this is what comes out to be qualitatively. You have a large particle, you have a small band gap. Well, that is bulk, and then large particle, and you have a small particle, you have a large band gap. So this is again the same picture I showed you initially. This is the small cadmium selenide nanoparticle with a large band gap, and that's a large cadmium selenide nanoparticle with a small band gap. In fact, if you wish to see the absorption spectra of these, you can see how it is shifting towards longer wavelengths. And this is the amount of time that I've kept the reaction for. Okay, so longer time allows bigger particles to grow, and the excitonic features, they shift towards longer wavelengths. Okay, so the band gap shifts to lower values as the particle grows. So does the fluorescence. Okay, these colors are typically representative of the colors that we actually see. But these are for nanocrystals or quantum dots that are more or less spherical. If you were to make nanoplatelets, and since we are going to discuss about 2D materials, let me tell you, if you're going to make these nanoplatelets, then these are very, very finely defined, whether they are 5 or 4 or 3 or 2, whatever, monolayers thick, right? And one can very easily purify them to get only 5 monolayers thick, only 4 mono. Here you have spherical particles, and it could be off by a monolayer plus or minus 1. It's not so easy to control in these cases. But over here, yes, it's very easy to control this. So the moment you have very pure 5 monolayer thick nanoplatelets, you see the emission is very much sharp. The emission full width at half maximum is less than 10 nanometers. Here, it's about less than 30 nanometers. Okay, so all these emissions are much, much sharper than the spherical quantum dots. Okay. So, having told you about all these basics about all these materials, let me come to some of the research on the transition metal dichalcogenides, which was started in my group by one of my students, Razi, who was a joint student with Ritu at NPL. Also with Sushma, who did a lot of time-resolved measurements on these materials. And the one that I'm presenting today is that of Shamim and Sushnata, who does a lot of photoconductivity measurements. He was a postdoc in my group. So molybdenum selenide. The way to make these, I've told you the detailed method of the high temperature. So what you do is start with heptamolybdate and make the acetyl acetonate of molybdenum. And this is now available off the shelf, so you can buy this directly. Heat it to a high temperature, inject the selenium precursor. Well, in this case, it's not trioctyl phosphate. It could be, but what we used was olyl amine selenium. Okay. So inject it and you get MOSE2 nanosheets. All right. If you look at most of the other methods, CVD or MB or exfoliation, then what you get is very neat looking triangular, sometimes more of hexagonal sheets. Very clean looking sheets. But when you look at the ones that we make, these are all crumpled sheets. You see this TEM image. And why they are crumpled is because all of this selenium precursor does not react completely, and there are a lot of defect sites that are created on the basal planes. And these defect sites The moment you have less amount of selenium on the surface, the molybdenum atoms below it are kind of non-bonded and they try to attract the nearby seleniums, therefore folding the sheet. And that's how all these crumples occur in the sheet. Okay, and these can be seen very clearly in the images. But I'll tell you that these defects are very, very useful for us in a moment. Okay. Well, we can control the thickness of these sheets. In fact, here I'm showing you 1 monolayer and 6 monolayer. And if you look at diffraction, 002 happens to be the growth direction. And you do not see any 002 peak when you have 1 monolayer. Of course, you cannot expect to have diffraction with one single plane. But this is a scan collection of 20 scans. Actually, it's also very difficult to see with 6 monolayers in a single scan. So with a collection of 20 scans, you do start seeing something. It's very easy to control the growth. So oleilamine is the capping ligand, which is also arresting the growth of nanoparticles, right? Because it's on the surface. So if you add a lot of it, then you get a low number of monolayers. If you add more of it, then the growth is allowed in this direction. Okay. And I was telling you about the quantum size effects, the excitonic peaks over here, the A and B peaks, they shift to higher energy when you go from 6 to 1 monolayer. Okay. Now, as I was telling you about the defects, these defects are very useful because these defects are much like the edge sites. And therefore, you can have enhanced catalytic activities or whatever activities that are dependent on edge sites. And one of these activities that we thought of was to use the sheets for hydrogen evolution reaction. And the way you do that is to take an electrode. And we used a glassy carbon electrode. You could take any electrode you wish like and put your material on top of the electrode. And then apply a voltage, the electron goes there. And if this electron is catalyzing, if the material is catalyzing, then the electron can be taken up and H plus turns into H2. And once that happens, the current flows and you can measure the current. So this is what is done over here. You take platinum over here, and instead of glassy carbon, take platinum over here. And then what will happen is that you should essentially get, without any potential, you should essentially get hydrogen evolution because platinum, for platinum, this is a normal hydrogen electrode in that case, right? And for platinum, it's 0 volts conversion of H plus to H2 or the other way around. But we get, because of all non-idealities and everything and the way we fabricate the device, we get about 100 millivolts. Well, everything is reported at minus 10 milliamperes per centimeter square of the surface of your electrode. Okay, so we get about 100 millivolts. Well, in case of molybdenum selenide 1 monolayer, the red one, we get about 210 millivolts onset potentials. Slightly more, 220 millivolts in case of 6 monolayer, and about 480 millivolts in case of bulk MOIC2. So, you know, this is precisely because the electron has to hop and tunnel across all these monolayers when you have multi-monolayers, but the electron has to just go across this monolayer. Intra mobility is what that counts when you have a single monolayer, and that is very high, right? The other thing is that the slope of this, the steeper the slope of this fellow, which means that I don't have to apply excess voltage and still I can get a lot of current, which means at a lower voltage I can get more hydrogen evolution. Okay, this is called the inverse of this slope is called the Tafel slope, and that is plotted over here. So the lower its value, the better the, well, it's not exactly inverse of this slope. Okay, it's a log scale. So anyway, the lower the value, okay, which means I can get more hydrogen evolution, and the value with MOSC2 is pretty low that way. Given the fact that MoSE2 is 60 to 70 times cheaper than platinum, I think one can settle for this. So these are very, very good results indeed with MoSE2. And the materials are very, very stable with time, right? And what it shows over here is exactly what I've told you over here, that it is more resistive for the charges to flow in multi-layers compared to 6 compared to 1 monolayer. These are nothing but impedance studies. And well, if we can replace platinum with MoSE2 and get such good results, why not replace the platinum elsewhere? And another thing that we work with are something known as dye-sensitized solar cells. Can we replace platinum there? And we'll try, but let me tell you something about solar cells. And well, this is what a solar radiation spectrum is like. So the yellow one is at the top of the atmosphere, and the red one is what you receive at Earth. So typically 3% UV, 44 visible, and 53 IR. So if you're going to think of some materials, you need to worry about where you want to place your materials and which solar spectrum you want to avail. And NREL publishes these charts regularly. Okay, they keep updating it. And it's a very, very busy chart. It essentially has every solar cell that has been tested, certified by NREL. So let me highlight on silicon. And that's what silicon's been like through its 50 years of journey. Well, and these are the most stable cells today in the market. Definitely you get 18% and even 23% if you're ready to shell out a bit more money. Another kind of solar cells are the dye-sensitized solar cells, and these are very easy to make in any laboratory compared to silicon, where you need a clean room fab and much more investment costs. But these dye-sensitized solar cells were first reported in 91 by Gratzel, and therefore they are also known as Gratzel cells. They have also come up from 4-5% all the way to about 15%. And based on the dye-sensitized solar cells were the quantum dot sensitized solar cell, which have also shown a very good increase in relatively shorter period of time. And again, based on similar approaches came up the perovskite solar cells, which also have a very steep increase, but all the absolute numbers are also very large. As I said, today you can get about 24-25% efficient solar cells of perovskite. The biggest problem is stability. But of course, quantum dots and dye-sensitized are much, much more stable than perovskite solar cells. The problem is that perovskite as a material, it is not so stable. That's intrinsic. So let me tell you something about how a dye-sensitized solar cell works and how it's made. So here you have a ruthenium dye, normally known as N719, because it has an absorption peak at 719 nanometers, and that's just the edge of visible. Okay, so very much in the very near infrared region. So you have the HOMO and the LUMO of this dye, and you excite an electron, take it up there. The electron is then taken over by titanium dioxide, which is then taken by fluorine doped tin oxide, which is a conducting oxide, which is a transparent conducting oxide, TCO for short. And on top of TCO, you deposit TiO2, and this is done simply by Dr. blading. So actually by rolling, a rolling pin method. You just put the paste and roll it. And then you dip it in the dye, and the dye gets adsorbed on top of this TiO2. This is mesoporous TiO2, about 20 nanometers. All these particles are, and so the dyes come in and get adsorbed everywhere. Okay, so the electron is taken up by this one. Now the hole has to be taken up by the counter electrode, and the counter electrode is platinum counter electrode. Okay, but how does it go to the platinum counter? There's a iodide triiodide redox couple. So what it does, platinum catalyzes this redox reaction. And so catalysis means it remains unchanged. So it takes up the hole and gives the electron. So that is how it's catalyzing. And well, so essentially the hole goes there, redox process occurs, uh, so oxidation process occurs, and then this fellow then reduces it back and takes up the hole. So this is what is done. So this is essentially the diagram of here. So what you do is take this TiO2 electrode and take another electrode with platinum on it, and then stick them together, drill a hole in it, put your electrolyte, seal it. That's it. Very easy to make. Okay. So if you were to replace platinum by anything, then it must catalyze this reaction, right? This redox process. And to see that, you look at something called the cyclic voltammogram. And these two peaks essentially are the oxidation and these two are the reduction peaks. And with platinum, blue one, and with molybdenum selenide, I see that both these oxidation and reduction processes can be catalyzed, right? The only thing is that platinum is more conductive, MoSe2 is less conductive, okay? And because of that, when we make these solar cells and we study the current voltage characteristics of the solar cells, then what we get is 8% efficiency with platinum and 7% efficiency with molybdenum. Well, we've not harped too much on the stability issues, but we did study for a few days, 5 days, and they tend to be decently stable. Yeah. Dye-sensitized solar cells are stable for years. All right. So these can be used for most of the places where platinum is used, so you can reduce a lot of costs. But then what ahead? Can these things be used for something else? Well, it becomes very, very difficult to explore other opportunities unless you go ahead and make some heterostructures. Okay. So MoSe2 is one such heterostructure which we can make. Well, of course, Shamim thought about this. And it has very low lattice mismatches. Both of them happen to have hexagonal crystal symmetry. Okay. One of them is semiconducting, the other is metallic. But if you look at these AB values, this is 3.29 angstroms, this is 3.79 angstroms, very close. Well, typically a mismatch of roughly 7-8%. So one could try and attend them. You know, when they are close, then you'll have less strains, and you can put one material on top of the other, and they bond. So you can have these heterostructures. So the way to make these heterostructures is essentially that you take molybdenum selenide nanosheets, and since you have a lot of defects, which are selenium vacancies, you put some thiol, dodecane thiol, DDT, on top of it. Okay, and this dodecane thiol goes and sticks to molybdenum because molybdenum is hungry for the chalcogen and thiol is sulfur. So then you put another one, cuprous iodide, which is also hungry for thiols actually. So this goes and forms these islands of cuprous sulfide on top. Okay. So if you look at the TEM, this is MoSe2, and this is, this is cuprous sulfide synthesized separately. But when you do it on top, then you get these kind of heterostructured materials, okay, all well characterized. There's another way to characterize these sheets, that is AFM, and it tells you that typically the thickness of one sheet is one monolayer is 2.8 to 3.6, about 0.8, 0.9 nanometers. And what you see over here is again the Raman spectrum, and this is your EG and A1G peaks. But then in our cases, we also get this huge peak in between, which is attributed to the defect sites. And when you passivate these defects, this peak goes down. So you do know how much defects you have, and whether you've passivated them, you've gotten rid of those defects. So that can be addressed by using Raman spectroscopy. You can do a lot more characterization and make sure that all these materials are indeed molybdenum, selenium, copper, sulfide, all are over here. And these are washed many times, so don't worry. They're not just physical mixtures or something. Okay. So if there are any free cuprous sulfide, they just come off by the washing process. So they are very, very nicely heterostructured. Okay. And that is also evident from the fact when you look at the X-ray photoemission spectrum of these materials, that molybdenum, you'll see two different signals, one from the molybdenum selenide and the other from molybdenum sulfur bond, which is from the DDT that is coming in. And one signal for selenium, one signal for copper. So selenium is bonded only to molybdenum, copper is bonded only to sulfur, and sulfur again has two signals over here, one bonded to molybdenum and one bonded to copper. Well, a bit of sulfur does get oxidized in the process because it is on the surface. And that always, I have told you that chalcogenides are prone to oxidation. Okay. Now, we have these heterostructures. What can we do with that? We still do not know what is the electronic structure of these heterostructures, and that's where our friend Shashwata from the physics department jumps in and does all the theoretical calculations. And this is essentially the sum of the summary of that theoretical calculations. And I'll show it over here in the schematic. This is the valence band for cuprous sulfide, and this is the valence band for MoSe2, and those are the conduction bands. So you see that the conduction band is lower in energy, and so the electrons go to MoSe2, and the valence band is lower in energy, and the electrons go to cuprous sulfide. The holes go to cuprous sulfide. So there's a natural separation of electrons and holes in these materials. So if there's a natural separation, then I could use it for a number of applications. I could use it for photovoltaics, I could use it for photocatalysis, the simplest one, photoconductivity, and one could make a photoconductive device over here. Okay, so all you need to do is take some silicon and put your material on top of it, put a barrier layer in between if you want. Don't do it if you don't want. Well, better results with a barrier layer. Put some gold for contact and aluminum for contact, back contact, and then you apply your voltage. When you do it in dark, then you see the levels are very, very low, all these solid curves. When you do it in light, under illumination, then if you look for MoSe2 only, there's a very slight increase, roughly about 24-fold increase. But for MoSe2 Cu2s, there's a 4,000-fold increase, and it's measurable. Not only that, this is not just visible light, but if you actually take a spectrum of the entire process, and you see this is also active in IR region, and this is very useful for space applications and defense applications. Yes, so with these IR active materials, and why they are IR active is because it's not Cu2s, but it's actually Cu2 minus X, and that's exactly comes to 1.97. So Cu 1.97s, as we've seen. And because of that, there are a lot of holes that get doped in the system, and these are active in the infrared region. Okay, and you get this infrared. You see, you don't have any infrared response with MoSe2. Okay, the devices are stable. Well, anyway, I'm not a device person, but this is in collaboration with Samit Ray from Kharagpur and Shubhendu Sarkar from SSPL. So they are very keen on making good devices too. Yeah, so you get some very useful materials over here. Well, again, coming back to our dye-sensitized solar cells, since cuprous sulfide has been used for quantum dot sensitized solar cells, we also tried to use these MOSE2 cuprous sulfide. And when you do MOSE2 cuprous sulfide, what you're gaining? You're getting a better conductivity because your charge carriers can move in the sheet, right? In cuprous sulfide, they would just go directly to the electrode and not be able to move so efficiently. So you get much better impedance values and therefore slightly better values for the efficiency. Of course, cadmium selenide is what we've used for these QDSCs, which are not the ideal materials. But anyway, you do get an enhancement in the efficiency. What else can we do with these materials? And again, look at the theoretical curve over here. Okay, so the green one is the projected density of states for cuprous sulfide, and that is the top of the valence band, as we've seen in the schematic. The red one is the projected density of states of molybdenum selenide, and blue is the total density of states. So at the bottom of the conduction band, it's essentially molybdenum diselenide. Cuprous sulfide hardly has any contribution here. So that is how we get these and put it on the energy scale. This is with respect to vacuum. And then at minus 4.44, you need to put the normal hydrogen electrode. And now you see, give it a slight potential. The working electrode, so the potential is between the normal, the reference electrode and the working electrode. Give it a slight potential and it comes at the same energy as the holes, and therefore the holes could be or electrons could be transferred here, or holes could be transferred here. And what does that mean? That means that this is very good if you want an oxygen evolution reaction to happen, and the mechanism is given there. And also, if you could push the potential in the other direction, you could transfer electrons from here. Okay, and that means if I'm giving electrons, remember H plus will take up the electron and make H2. So it's very good for HER. So essentially this material in principle could be used for both OER and HER, which means it could be used to split water. Okay. But OER happens better under alkaline conditions, and HER, H plus is going to H2, would be under better under acidic conditions, but it does happen under alkaline conditions, and here's the mechanism over there. Okay. Well, I don't need to describe the mechanism, but later if you have some questions, we can come to that. So looking at the OER reaction, look at this one. The pink purple one is iridium oxide, which is the industry standard. Okay. The blue one is molybdenum selenide, cuprous sulfide. And you see that our material is pretty much good, as good as IRO2, not too bad, except that you need a slightly higher voltage. Again, iridium is very, very expensive. So again, the Tafel plots showing that these are pretty decent materials, resistivity data. Okay, again, the stability. Now we've also done stability tests for 24 hours. It continues as a very efficient catalyst. But the only thing that happens when you do this catalysis and then you again record the X-ray photo emission, you see copper gets oxidized. So if you remember, copper had only one peak. Now it gets oxidized into copper 1 and copper 2. Okay. But the XRD does not change. XRD remains the same, which means our material has not changed, but on the surface, since X-ray photo emission is a surface phenomenon, on the surface, things have changed. And what is that? Copper 1 and copper 2. So earlier I had only copper 1, and now I also have some amount of copper 2. Well, almost similar amount of copper 2. So based on all these results, we proposed the mechanism over here, which was shown earlier. that you have some copper 2 sites and copper 1 sites. And then OH minus goes and attacks the copper 1 site, which is free. So both of these sites are now copper with OH. And another OH comes and attacks, okay, and takes out this H plus. So now you have copper with O. Another OH comes and attacks, and it forms OO bond, OOH, the peroxide. And then, since this peroxide is there, we can get rid of this H plus using another OH minus, and then you have O2. Okay, when this O2 dissociates and free oxygen is released, copper 1 comes back to its state. So this is our proposed catalytic cycle, and this is also calculated by Shashwata to be a low energy pathway. Okay, a very interesting calculations when you draw all these and you make all these structures and do all these calculations. So it comes out to be a very low energy pathway. The same we can do HER. As I had shown you earlier, it was about 200 millielectron, slightly less for the heterostructure, 190 millivolts. But in case of alkaline condition, it goes all the way up to 400 millivolts. So slightly more potential is required. But then hydrogen evolution does happen in the alkaline medium as well. And again, this is energetically feasible too. Okay. Well, Shashwata went ahead and calculated some more heterostructures since we were working on cesium lead bromide. And again there, so this is all the DOS and well, essentially focus here. He says that again, look, this is a type 2 heterostructure. But to make it experimentally, MoSe2, Cu2s, they were both hexagonal, we could do it. If you look at cesium lead bromide, then it's a cubic structure. And how does one make a heterostructure of MoSe2 with a hexagonal and a cubic one? There's a lot of mismatch. Okay, so Shamim came up with this bright idea that, okay, we can't make a heterostructure, but let's try to make one by using a linker molecule. And he took 4-aminothiophenol. So the thiol is definitely hungry for these defect sites on MoSe2. And the amino group is one that caps the perovskite nanoparticles. So once you've attached the thiol, then you put in some perovskite, and that goes and gets attached over here. So if you look at sheets and then perovskites alone, and these are the attached ones. Okay, of course washed and well characterized. I'll just skip that. What happens also is that there's a fluorescence of cesium lead bromide at about 515 nanometers. And when you attach ATP, when you attach the two ATP, fluorescence, because the charges migrate from here to MoSe2, from the perovskite to MoSe2, and quenched when you attach. When you just throw them in solution without ATP, it is also quenched, but not to such a large extent. So you know that these are really attached particles. Also, if you look at the time resolved fluorescence, the same quenching behavior can be seen because the fluorescence lifetime becomes much shorter in case of the attached particles. Okay. And again, try to make these photoconductivity devices. And the very nice thing with cesium lead bromide is that these curves are very, very flat. So no matter at a small voltage also, you can do your detection. For cuprous sulfide, you had to come to about 2 volts. But here, even at very small voltage, you could do your measurements. Also, the fact that cuprous sulfide, the on-off difference was about 4,000. Here, the on-off difference is about 20,000. Okay, So you have a much more gain in these cases. Also, there's a slight photovoltaic behavior. You see, it doesn't go to zero at zero. And these are very stable devices. The only downside is that cesium lead bromide is not active in the infrared range. Okay, there's a lot more that we can do with all these, but I think my time's up. So let me summarize that we mostly worry about energy, whatever we want to do with it. We convert or store or use or dispose. And nanomaterials, in particular 2D, are very advantageous for these applications. And I've shown you some of the applications. And we do work on a lot of heterostructures. Maybe some other time I could discuss the other ones that we work on. Okay. And now we can even make heterostructures when the crystal structures are completely different. In fact, you saw the case of linking with ATP. We've tried with a lot more materials now. And we've also tried to make van der Waals heterostructures, which we're going to publish very soon. The only thing we lack, and it is on the way in our central research facilities, are transient absorption and ultra-fast measurements. And that is what we need in order to gain, to have a good understanding of what is happening in the excited state and therefore gain more control over the properties. I believe the road ahead is that one should go for more 2D materials, more heterostructures and interfaces. The interfaces are hardly understood, and one has a lot of space over there. One needs to explore them, understand them in order to do some very good work. And let me thank again my group and all of you who've been so patiently listening to me. Thank you so much. I'm open for questions.
Thank you very much, sir. You have given a wide insight of nanomaterials, especially for photovoltaic or photoconductive materials are there. And in our DTU we have a energy center is there. They are working on solar energies, so that is a one part of it. But without going inside the foundation of the material which we are using to trap the solar energy, without your understanding, is not possible to improve our energy trapping or using for further, you can say nowadays, solar or battery based transportation system. So I hope this will give insight of nanomaterials, how they are constructed, how they are used to trap the energy at nanoscale level. So just now a session is open for any queries there. So just I would like to ask a very simple question for my understanding. Uh, Let us say when we have a temperature changes are there, so the efficiency of photoconductive material is changes, or may you can develop some phase change material that retain the efficiency of energy trapping. Sir,
Yeah. Yeah.
yeah.
So there are effects of temperature on all these charge carriers, definitely. They get more randomized when you go to higher temperatures, and therefore the efficiencies do drop down. Well, now one thing that I'm not a device person, so I'm not really looking at the efficiencies per se. What I do look at are different materials, but how to enhance the efficiencies, yes, but how to stabilize the devices is something which I have not worked on.
Just because this platform I would like to provide just to interact our researchers or participant to go inside how the material actually synthesis which we are using. So just I am asking again a very simple one: a phase change material. Uh, can be, or the phase change a property in a photoconductive material can be possible to incorporate it?
Sure, I mean it should be possible, but again, I'm not the right person to answer that because I do not have experience either with phase change materials or so much with devices.
Yeah, okay. Um, it's open to further any queries there.
Yes, sir.
Yeah, go ahead.
Good morning, sir. This side, Neeraj Kant. Sir, I have a question regarding organic solar cell.
Yes.
Sir, molybdenum disulfide can be used as electrode in organic
Yes.
solar cells. And what about the effect on stability and efficiency in organic solar cell?
Okay, again, what is the electrode that people use with organic solar cells? Do you know that?
Yes, sir.
What is it?
ITO, aluminum.
Yeah. So, what is the electrode doing? The work of the electrode is to catalyze something, right?
Yes, sir.
And again, as I've shown you, that if you want to use any material in place of the material that is being previously used, the first thing is to look at the catalytic activity, right?
Yes.
If the same catalytic activity can be performed by this material, then go ahead and use it. Why not?
Okay.
Right?
Thank you.
Now, organic solar cells, of course, there are so many different kinds of organic solar cells. So one has to really look at what exactly it's catalyzing. So in case of organic solar cells, it's an electron transport layer and a hole transport layer, right?
Yes.
So one has to look at that P dot PSS or Spiro or whatever you use in your, I mean, there are so many different kinds of PCBM. So one has to see if it can catalyze the transfer of electrons or holes from those materials.
Yes. Thank you, sir.
Welcome.
Any other query? Okay, hope I think no further queries there, because at least we can get a flavor of our material chemistry, because in engineering we read a little bit of crystallography, material science,
Yeah.
so that they can correlate when we are talking about a clean energy manufacturing, from where it start. Actually, it start from material. So sir, thank you very much on the behalf of Atal FDP AICT body, we would like to thank, and on the behalf of Department of Mechanical Engineering, Delhi Technological University, we would like to uh, appreciate your valuable time giving to this expert lecture. And I hope students or participants, researchers, faculty will get some new insight to look at when we are using materials in our application, especially uh, energy storage and solar energies are there. So thank you very much
Thank
again.
you. Thank you. Thank you for the invitation again. Okay. So I'll sign off now. Is there any
Yeah,
more
sir.
questions? Okay.
Any further question is there, Deepak?
No, sir, I didn't receive any further questions.
Okay, okay, that's fine.
Okay.
Thank you,
Thank
sir.
you.
Thank
Thank
you
you
Thank
very
you
so
so
much.
much.
thank you, sir.
Thank you so much. Yeah.
Our next lecture will start at 11:45. The expert is Professor Pradeep Kumar from IIT Roorkee. So please be online at 11:45. Thank you, everyone.